Now let's discuss Coulomb's theory of active and passive earth pressure. This theory was introduced by Coulomb in 1776, making it historically older than Rankine's theory. Coulomb assumed a planar failure surface and importantly included the effect of wall-soil friction, a key difference from Rankine's approach. Coulomb's theory is developed for cohesionless or granular soils, and it considers a general case with both a sloped backfill and a sloped wall. In the figure shown below, alpha is the inclination of the ground surface with respect to the horizontal, theta is the inclination of the wall face relative to the vertical, and delta is the wall friction angle between the wall and the soil. The value of delta typically ranges from 1/2 to 2/3 of the soil's internal friction angle, or Phi', depending on surface roughness. The resulting formulas for Coulomb's active and passive pressure coefficients involve trigonometric relationships and depend on four main angles: Phi', or the soil friction angle, theta, the wall inclination, delta prime, wall soil friction, and alpha, ground surface inclination. One major difference between Rankine's and Coulomb's theories is the presence of wall friction in Coulomb's method. Rankine assumes a smooth wall with no friction, whereas Coulomb allows for interaction between the soil and the wall. For a special case with a flat ground or alpha equal to 0, a vertical wall or theta equal to 0, and 0 wall friction angle, Coulomb's formulas reduce exactly to Rankine's results, as you can see in this slide. A practical example illustrates the effect of wall friction. If Phi' is 36 degrees, delta be 24 degrees, alpha be equal to 0, and theta be equal to 0, then Ka for Coulomb would be 0.178. while Ka for Rankine's theory would be 0.260. This shows that including wall friction reduces the active pressure on the wall, which can lead to more efficient retaining wall design. Or we can say that Ka for Rankine is more on the conservative side. In this slide, we will talk about the concept of equivalent fluid pressure, or E.F.P. Since lateral earth pressure is typically distributed in a triangular shape, similar to fluid pressure, we can simplify the analysis by imagining that the retaining wall is being loaded by an equivalent fluid instead of actual soil. In this approach, the unit weight of the equivalent fluid is equal to K times gamma, where K is the lateral earth pressure coefficient, which can be at rest, active, or passive, and gamma is the unit weight of the soil. Let's look at a practical example. Suppose the soil has an internal friction angle of 30 degrees and a unit weight of 120 pounds per cubic foot, or PCF. Therefore, the lateral coefficients like K0 would be 0.5, Ka would be 0.33, and Kp would be 3. Now, to calculate the equivalent fluid pressure, we can multiply each K by value of gamma, which is 120. And therefore, E.F.P of at rest pressure would be 60 psf, E.F.P for active pressure would be 40 pcf, and E.F.P for passive pressure would be 360 pcf. This gives engineers a simpler and more intuitive way to visualize how much pressure is acting on the wall. For example, in the active case, the E.F.P is 40 pcf. This means that the soil in this case applies less lateral pressure than water would, which might be surprising at first. But it makes sense when we consider that soil friction reduces the lateral force acting on the wall. For your information, gamma of water is 62.4 pcf, which is larger than the E.F.P for active case in this example. The concept of E.F.P was first introduced by American Association of Highway Officials in 1950s, particularly for the design of highway bridges. They recommended using a minimum value of 30 PCF in design calculations to ensure structural safety and to simplify analysis. Now here is an interesting question. If the E.F.P for the active case is 30 PCF and the unit weight of the soil is 120 PCF, what would be the corresponding friction angle phi? So we begin by calculating Ka. Ka times 120 should be 30. This means that Ka should be equal to 0.25. Next, we can use Rankine formula for active pressure and say that 1 minus sine of phi divided by 1 plus sine of phi should be equal to 0.25. This gives that sine of phi should be equal to 0.6, and which means that phi should be approximately equal to 37 degrees. So to produce an E.F.P of 30 PCF, the soil must have a friction angle of about 37 degrees. That is actually a relatively high value, which suggests a dense and well-compacted granular soil, such as gravel or coarse sand, not a loose or soft material.